Okay, good afternoon, everybody. So let's get started. I am DK Panda from Ohio State University, and my colleague Dr. Xiaoyi Lu will be presenting this session. It is titled DLoBD, an emerging paradigm of deep learning over big data stacks. As we have been hearing in a lot of these talks, starting from the keynote talks in the morning, the deep learning is becoming very hot. And it's basically, as many of you might be knowing, it is a subset of machine learning. And it is going through a lot of resurgence because a lot of models are available, a lot of data is being made available, publicly available data sets like MNIST, CFAR, and ImageNet. There is also a lot of capabilities are upcoming, especially from the high-performance computing side. And then people are ready to not only process big data, but also try to run deep learning on top of the big data. So what do we mean of that? Mean by this deep learning over big data? So think of like just a very simple, like here, flickers, magic view photo filtering. So you can see that if you have a large set of images, can you actually automatically categorize them into different classes? You might have a billions of pictures, then using some deep learning, you should be able to exactly see, like in this case, what we are trying to show, like a sunset, kind of, and the landscape, you can categorize them easily. But more important thing, this is the workflow, or this is the pipeline. I think we heard many of those kind of instances in today's morning keynote talks. So that means if we have a kind of a pipeline, what you see here, like this is a typical Flickr DL and ML pipeline, we might be trying to have preparation of the data sets at scale. And then we might be trying to run like a deep learning with scale like a Tensorflow. Might be we can be doing some non-deep learning analytics also at scale, which is through Spark. And then finally, we might be applying some machine learning techniques or the models using the Apache Spark. And the whole idea is that can we have a convergence, or can we try to run it on the exactly same framework or same pipeline or on the same hardware so that we can get better data locality, and also we can have efficient resource sharing and cost effectiveness. And as many of you know, these days, like again in this summit, we have been hearing about a lot of these deep learning models and stacks like Caffe on Spark, SparkNet, TensorFlow on Spark, TensorFrame. So many of these, as you can see, that they are combining both the deep learning aspect as well as the big data stack. So that is what exactly is the focus of the talk. Now, if you take a look at how these things, the stacks are running, so this is trying to show a hierarchical picture, like starting from the very top, we have deep learning models and algorithms. Then after that, we have the deep learning libraries. Then we have the frameworks, resource scheduler, then file systems. And then at the bottom, they are running on the high-performance networks and computing units. Now, the question is, of course, the HPC systems are giving us a lot of performance. But as it goes through all the different layers, can we actually, in a practical manner, deliver that kind of a performance and scalability to the top layer? So that is the kind of the biggest challenge we need to worry about in this emerging paradigm. And most of us know, like we are seeing a kind of a convergence between these three fields, HPC and big data and the deep learning. As the HPC environment is providing us more capability, big data environments are able to take care of that or take advantage of that, and then the deep learning, we are trying to take advantage of the big data, and the cycle continues, and we want to have the best and best performance and scalability. So now let's take a look at the details, what exactly is happening, where the actions are. So if you see in this picture, on the left-hand side, we have the big data stacks, like typically running on distributed file systems like HDFS, or resource scheduler using Yarn or Mesos. Then we have the big data frameworks, Hadoop and the Spark. The right-hand side is the HPC. So this is where we try to see like a multi-core CPUs, GPUs, also high-speed networks like RDMA, the remote DMA mechanisms of InfiniBand, Rocky, iWarp, those kind of environments, and also like a GPU direct RDMA. So in this context, already a lot of convergence is taking place between HPC and big data. These are the two pillars. What we see, like BLAST libraries, a lot of optimizations are happening with respect to math operations like Atlas, OpenBLAST. NVIDIA has the CUBLAST, Intel math kernel library is also being optimized. Then in all these deep learning frameworks, it is the heart of the convolutions is the most important one. So NVIDIA has the CUDNN, and also Intel MKL as of the DNN. And then to help with these kind of activities, then the HPC environments are providing the mechanisms like RDMA, and the other one is GPU direct RDMA, where you can actually move data from one GPU to another node or another GPU over the network directly without going through the host. So with that kind of a background, this talk will focus on three things. First of all, how we accelerate the big data stacks, and then how do we benchmark and characterize the deep learning over big data stacks, and finally, how we can accelerate the DL over big data stacks. So with respect to acceleration of the big data stacks, so this is a project in my group we have been carrying out for last almost 5 years. This is called High Performance Big Data. The URL is hibd.csc.ohiostate.edu. So what we have done over the last 5 years, we have really brought the convergence between the high performance computing and big data. So if you take a look at like the Spark or Hadoop or HBase, Memcached, these are the kind of the big data stacks. We have actually accelerated those using the modern RDMA features of networks like InfiniBand, Rocky. These stacks are also run on Ethernet, so this is like a superset of the Apache stack, and you should be able to get very good performance. I'll try to show you a little bit later. Currently, is being used by these libraries are being used by more than 285 organizations from 34 countries. These are based on voluntary registration. Anybody can download, but some of the organizations identify themselves as users, so this count is based on that. And we have more than like 26,000 downloads from our site. And earlier we started this project with mostly x86 platform, but as many of you know, the newer kind of open power platforms are coming up, so we have supported for both. And also, as the cloud computing is becoming very common, we have also provided support for Singularity and Docker. So if you have any kind of requirements or environments, I'll strongly encourage to download these libraries and then try to see how you can get higher performance and scalability. This is trying to just show very quick like a timeline and downloads over the years, steadily all our releases being gradually more and more being used. So just to give an example how our design works, so let's say we focus on the Spark and how we have done the RDMA-based Apache Spark. So as you can see, like let's say the x-axis, we are trying to show the basic Apache Spark versions, like the 0.91, 1.2, 1.31. We started the research. The first paper was in the Hot Interconnect 2014. We had the initial design of the RDMA-based Apache Spark. So as you can see that the default design choices, there were like hash-based shuffle and IO-based data transfer. Then as the choices kept on being enhanced, we also kept on adding our RDMA support on top of those mechanisms. And then in the 2016, we had a big data paper. So there we introduced newer kinds of interfaces, also in the next slide, so that we can keep the compatibility with the Spark, but at the same time, try to give you much more higher performance and scalability. And as the field now is moving towards the deep learning, as we have been hearing, so that is our next step to really take advantage of these newer modern deep learning frameworks and then try to run it over Spark. So this one is going to show the more internal designs of our RDMA-based Spark. As you can see, like this is the traditional stack has all these different block transfer services, like it has the native server, NIO server, native client, NIO client, and mostly it is the communications are going through the Java sockets interface that is over the traditional Ethernet, or you can run it with TCP over IP, like on the InfiniBand network with the IP over IP protocol. So the right-hand side is actually trying to show how we have actually done the design. So we have the RDMA-based design communication engine sitting here, and we have introduced RDMA server and RDMA client, and then it is going through the JNI, and then trying to, internally we have a lot of designs like RDMA-based shuffle, SCADA-based architecture, dynamic connection management sharing, non-blocking data transfer, also JVM heap buffer management. So with those kind of things, we are able to really deliver very good performance on RDMA networks. So this is the latest version for the RDMA for Spark distribution. So here you can see that all the features which are highlighted in the red. So our latest release is based on 0.95, and it is based on the Apache Spark 2.10, and we are currently updating it to the later version. The one thing we need to just highlight that we are keeping the API compliant. So we are not changing anything below. It is mostly the acceleration the communication. That's what is taking place here. And these kind of packages are also being deployed. So in this case, like we have the HybridD packages on San Diego Supercomputing Center. They are our collaborator. If you have like a NSF Exceed account, then you should be able to directly run there. We have direct appliances available there. The same thing is also happening on like a Chameleon Cloud, which is a NSF-sponsored cloud testbed. So these appliances are there. You should be able to directly use those appliances. In fact, you do not need to be built. But if you are an ISP provider or if you have your own system, you should be able to just download and use it to get the performance. Now, what kind of performance you see? So this is trying to show some very sample benchmarks, like this is on the San Diego Supercomputing Center Comet. If you take like a common benchmark like HighBench, so what we are trying to show here, there are like the orange lines, the bars, and then the red lines. So the orange bars, so both of these experiments on the left side as well as right side are running on the same InfiniBand system, but one is running through the orange one is going through the TCP IP over InfiniBand, that is the IP over IB stack, which is not very efficient, whereas the red bar is actually going through the RDMA designs. So that is our new stack. So as you can see here, like we are able to deliver performance benefits of like 37%, 43%, even up to like a 1,500 cores. So you can have the same hardware, but using the hour stack compared to the default stack, you should be able to get more higher and higher performance. So with that kind of a background, now let me hand it over to Dr. Lu. So he will try to focus on the benchmarking and characterization and how do we accelerate the DLoBD stacks.
Thanks. Okay, so Dr. Panda just to give a very quick overview of how to utilize high-performance networks, especially with remote direct memory access feature, RDMA, to accelerate big data stacks. We gave example about how to optimize Spark. So the next one is actually our major focus of this talk is how we can run deep learning on top of Spark, and also take advantage of high-performance networks capabilities. So here we choose 4 examples, like this, like the most 4 popular ones based on our study. One is Caffe on Spark, or Tensorflow on Spark, or MML Spark, which is CNTK on Spark, essentially, actually. So BigDeal is Intel big deep learning solution on top of Spark. So before we start this work, we actually trying to understand how we can actually run experiments and also make those experiments or results make sense of those results. So broadly, we actually trying to analyze from 4 different angles. The first one is what kind of deep learning workloads or data sets we should choose. For example, we see that, if you're new or just like us, if you want to explore on this direction, what you should have in mind is that there are different sizes of different kind of models. So for example, some model maybe just very shallow, some models very deep, and also the parameters size of the model is quite different. So it's better to choose different kind of model to benchmark the stack. Another thing is, of course, a lot of different kind of data set available. And also you can combine any of this model and the data and run the experiments. And then the other thing is like choosing the representative DLoBD stacks. So like I mentioned, we choose the Caffe, TensorFlow, CNTK, and the BigDeal on top of Hadoop, Spark, this kind of environment. And also we want to, through the for the characterization perspective, we want to run these stacks on different kind of processors like GPU, CPU, and the different kind of network transmission protocols like RDMA, including or IP over IP. And also another thing is we also want to see what kind of architecture difference between these stacks and how they actually do the model training and the model synchronization. So finally, we also want to see that what kind of numbers you can show, because these days different people actually show different numbers. So some people say that I can improve like a 10x, or some people say that I improve like 20%. So what's mean by those numbers? We need to have a very clear understanding of those stuffs. So with this, let me first introduce the architecture of Caffe on Spark. Some of you, if not familiar with it. So this one is just like this figure shows. So whenever the Spark driver, you can think is kind of, you can launch your application in one of the Yarn container, and then that application will get submitted to the Spark cluster, and then multiple Spark executor get launched in the nodes, right? And then the Spark executor will try to load the Cafe core, and then the Cafe core will run the model based on the construct RDD. And then once the model local training finished, you need to do the model synchronization. They have a module called the model synchronizer. And then this model synchronizer supports both RDMA and the TCP/IP-based communication. And then once the model training done, or once you finish all the epochs you configured, then the model you can save back to the HDFS, those kind of things. The benefit of this kind of architecture is that the Spark can help Cafe to scale out to multiple nodes. And also, your data can be shared on the HDFS storage layer, so that just like Dr. Panda mentioned earlier, right, you have multiple phases in your pipeline. Then if later on you want to run some other stuff based on data, or you want to reuse this model, you can get those data or those models directly from the HDFS layer. This is pretty good architecture from the pipeline perspective. This is the Cafe on Spark. For TensorFlow Spark, similarly, they choose the same kind of strategy. The only difference is that for TensorFlow Spark, because TensorFlow by default is using parameter server-based approach, so they will choose one Spark executor running, not one, I mean, depends on how many parameter server you want to configure. So choose multiple of them to run as a parameter server, and then the other executor will run as the TensorFlow worker, okay? So those workers we're trying to train the model, and then once you get some new weights, you're going to communicate with the parameter server through gRPC or gRPC plus X approach, okay? So in the community, people trying to contribute different kind of X. For example, some people have verbs-based support, some people contribute MPI-based support, those kind of things are available. And again, they're trying to use HDFS Yarn in the whole environment. So the third one is CNT and Spark. The whole architecture is still similar. The major difference is that because CNTK by default, all the communication they actually implemented with MPI. So those kind of like communication are actually implemented by MPI runtime. So it depends on which kind of MPI runtime you choose. The underlying communication will be different. For example, if you choose the MRPH2, which developed in our group, it has the old RDMA support in the MPI library. So you don't have to do any more designs on it. So this is CNTK on Spark. The last one is BigDeal. This was developed from Intel. So this one is very different than the earlier three solutions. The earlier three solutions, actually, if you look into their architecture, you'll see that, okay, actually this is just a kind of integration from different packages. For example, either CNTK, TensorFlow, and Spark, and then there's kind of communication layer make them collected. But BigDeal is kind of organically designed with Spark. The major idea is that in the Spark code, right, there's a block manager which kind of take care of the communication. Like, for example, if you want to transfer blocks between different nodes, you can, essentially, you need to involve block manager. So the idea of BigDeal is that can we like redesign block manager as a distributed parameter server, okay? So then in this way, we can actually take advantage of optimization in Spark code to help my parameter server, right? For example, in this case, like earlier we mentioned, if we can make the RDMA design integrated into Spark, then this BigDeal stack can utilize the RDMA-based block manager directly without any change. So this kind of some benefit from BigDeal. So we call this kind of approach in-band communication. The earlier three actually is choosing out-of-band communication approach. So like I mentioned earlier, you can choose a lot of kind of different data sets as well as models to train and test these stacks. We choose like MNIST, CFR10, ImageNet, and then different models like NetNet, CFR, then Quick, VGG, AlexNet, or GoogleNet, or ResNet 50 to do the experiments. Let me show you some of these numbers. So first of all, we want to compare that if we run this kind of stack on top of either CPU and the GPU, and for CPU, you can choose OpenBLAS or MKL, Intel MKL solution, or for GPU, you can directly run on top of GPU or GPU plus CUDA-DN. So as we can see here, in most cases, the GPU plus CUDA-DN give you the maximum benefit. For example, if you look at the first set of bars in one node, If you choose GPU plus cuRDN, and then you can significantly reduce the training time, end-to-end training time, like 98%. That's a big improvement, right? So this, and also if you increase the number of nodes for this smart and quick experiments, you already see that GPU will win. Now this is why also NVIDIA these days get a lot of market from deep learning domain, right? But in the meantime, Intel guys is also trying to say, okay, Intel processors plus MKL solution actually can also help in some cases. Actually, we also find in some cases, for example, in the NONET on MNIST, we see that the CPU plus Intel MKL 2017 actually give some good benefit compared with GPU. So this actually means that if you have GPU, of course, you can get some good benefit for deep learning workloads. But if you only have CPU, doesn't mean that there's no chance to get some benefit. You can still do very good job with deep learning workloads. So those just comparison between different kind of processors. And now we are trying to run the exactly same experiments on top of different kind of network protocols. Here we run Hadoop Spark and Tensorflow Spark on top of the latest generation of InfiniBand, which is 100 Gbps per second speed. And we are going to compare both IP over IP and RDMA protocol. As we can see that once you go beyond more than like 8 or 16 nodes, you will see that the RDMA protocol definitely give you some very good performance benefit. For example, if you just look at the NONET on MNIST, compared with IP over IP protocol, for 16 nodes, the execution time get reduced by 45%. That's a very big gain, right? And then for the TensorFlow, similarly, for some model, actually, we can see around 33% improvement, but some model, we only see 5%. Actually, later on, I will introduce why sometimes the benefit is not that much. And then that is about Hadoop Spark and TensorFlow Spark. For ML Spark, similarly, here, if the solution of GPU plus cuRDN performs best for ML Spark, and we see that up to 55x faster than CPU plus OpenBLAS. That's a very, very good gain, okay? But the ML Spark, by default, it just runs with cuRDN. So here we don't have the regular GPU numbers. And for CFR10 numbers, we see that for both MPN and RDMA, both RDMA protocol and IPRB protocol, the numbers looks a little bit similar. Here, the major reason is because the model and the data set is a bit small, so the communication may not play an important role in this case. But if you run some larger model like VGG, you definitely will see some difference. Okay, so those kind of performance just from the end-to-end perspective or overall performance numbers. Now, sometimes from deep learning guys, they may say, okay, this number may not make sense to them because without talking about accuracy, if you just show performance, doesn't mean anything, right? Sometimes. So here we're also trying to say that, of course, you need to also pay attention to the accuracy curve, okay? So here we just want to compare IPOB and RDMA curve on top, in the perspective of accuracy, when you can achieve 70% accuracy, okay? Here we run NextNet on ImageNet with Hadoop Spark or GoogleNet on Hadoop Spark or VGG on with BigDeal. So here we see that in both of them can achieve a similar kind of accuracy for 70%, but RDMA protocol can reach there much faster. Okay, for example, in the BigDeal case, they can reduce the training time around 48%. That's a big improvement, actually. Okay, so another perspective actually is deep learning is worried about accuracy and also training performance. But from system researcher perspective, we also want to see whether resource on the cluster being utilized efficiently or not, right? I may more worried about whether my CPU, my memory, my GPU, or network bandwidth is being utilized efficiently. Actually, what we see is that all these frameworks, they actually not utilize all the resource very efficiently for the current generation designs. For example, let me just take one example for the right side, the network bandwidth utilization, okay? Here we are using the IBEDR, which essentially has 100 Gbps per second bandwidth. But actually, no matter RDMA or IPOB, currently with their design, they can only achieve like a 20 megabyte per second throughput of the network, which means actually there's a big room we actually can improve the performance. Okay, so this is some different perspective. Another perspective I want to highlight is that earlier we mentioned that, right? For DLoBD stacks, it's good. You can run everything on single pipeline, on single stack. But the problem is that there are a lot of layers for you to run your deep learning jobs, right? There's a file system, scheduler, and a Spark execution engine, and then to your deep learning library. So some people may be interested that, okay, if I run some job on top of, let's say, TensorFlow on Spark, compared with if I run directly on TensorFlow, how much overhead are there because of the number of layers, right? And how much portion of time actually spent on different layers. Here we actually did a very good breakdown study. We are trying to show that in some case, the Yarn overhead, like scheduling plus the Spark execution layer, actually has some overhead. It can up to like 15% time get spent on these two layers. And then if you look at the actual training, the training time is similar to the native TensorFlow. So this basically means that if we can further optimize these different layers, and then we can try to reduce this overhead in all these layers, this DLoBD stack will become more efficient for the next generation deep learning workloads. So with this, let me later on another section we are trying to see that we are trying to explain how to further optimize the native TensorFlow with RDMA protocol as well. So that's why I put a circle highlight this one. So here I just want to we show a lot of numbers, but I want to give a summary before I go to the next topic. So of course we see that RDMA protocol deliver from the high performance networks can benefit deep learning workloads based on a lot of numbers we showed here. But sometimes we see very good performance improvement, but sometimes we see less. So the major reason is because, okay, if you're, this totally depends on your model size when you do the model synchronization, especially how many parameters values you are going to synchronize. And also RDMA can scale better and utilize resource more efficiently. For example, if you see the network utilization, RDMA can get utilized network much better than IPLB protocol. And then GPU-based deep learning can outperform CPU-based version, but not always. Based on the results we showed here, we see that a lot of opportunities for further improvement. And also we see that we need a lot of more benchmarks as well as public data sets to analyze these stacks. Next section, I want to try to give some quick overview of what kind of optimization we can further do in these stacks. One thing is, like I mentioned earlier, in the BigDeal, because it's tightly integrated with Spark, if we can optimize anything in Spark, especially backend shuffle architecture, we can get a very good benefit for BigDeal applications. Here, the example is the RDMA Spark we showed earlier. So we just run the BigDeal on top VGG in like SDSC commit cluster. We see that around 2.6x performance speed up, but we keep the similar accuracy curve, okay? This is epoch level evaluation. And if we go to scale, we see that the RDMA has very good scalability curve, but IPLB sometimes not running pretty well. And the TensorFlow, because it's partner server architecture, yes, we need to be very careful about their communication engine because all the models need to synchronize from their gRPC protocol or other protocols. So here we are trying to show that if we can redesign our gRPC engine with RDMA protocol, we are able to show very good performance improvement. Here we see for different kind of message size up to 8 megabytes or even larger, we show around more than 2.5x performance speed up. And then we also compare with other different solutions available in the community currently. Our gRPC plus RDMA approach can achieve up to like 40% improvement compared with other channels. And this was ResNet, and then this was Inception. And then with this, let me conclude this talk. Overall, we discussed challenges and opportunities of run deep learning on top of big data stacks. We agree with the keynote speakers today. We are trying to, we also envision that in future there should be a unified runtime, but to support all kind of deep learning workloads. But the problem is currently, if we just naively integrate them, it's not the best design for sure, because we see a lot of kind of overheads, and so resource utilization is not perfect. This means we have a lot of research opportunities for future designs. We actually organize a workshop. If you are interested in these type of topics, please feel free to contribute in the future events. With this, let me thank all of you, and we're happy to discuss with you. Thanks.